Okay, I'm continuing to read Planetary Core and Surface Temperatures by Douglas J. Cotton, a paper published in 2013 in the SSRN Electronic Journal, and I skipped forward to section 6. The reason I skipped forward to section 6 was because I was kind of getting a little bit tired of reading misrepresentation of what the greenhouse gas theory actually was, and I wanted to find out what his actual theory was instead of to try to get an idea of where he was coming from. And where he's coming from is essentially well, let me give the thought experiment that I was describing earlier. We took a cubic meter of air at the tropopause at 10 kilometers above the Earth and allowed it to drop to the ground at 0 kilometers, and I found that when I did this process, there was approximately a 98 Kelvin difference, that the air should heat by 98 Kelvin if that were done. And I made some arguments that that should not actually be the case. I'm actually coming around, though. I'm actually coming around to this argument, and I hope you can see why that I think this might be the case. That maybe this idea as actually does hold some validity, and we don't want to dismiss a valid idea in the defense of another valid idea. So this idea is, I think this idea is valid, actually, but we don't want to dismiss the idea of greenhouse gases just because this idea is valid. I'm going to go through kind of back to that Wikipedia article. And the Wikipedia article contains something called the mathematics of the adiabatic lapse rate. And what I'm going to do is kind of go through this equation here, P dV equals negative V dP over gamma. And what I did is I took Wikipedia's equation and put it next to my equation, and essentially this equation and that equation are a match. This is the equation, kind of a differential form of the adiabatic relationship equation, and I said yes, that does match. Then that is followed by this equation, and it says the first law of thermodynamics can be written mc sub v dt minus v dp over gamma equals 0. Now I wanted to see if I believed that were true, and what I did is I wrote the first law of thermodynamics being the change in internal energy of the gas is equal to the heat added to the gas plus the work done on the gas. Then I solved that for Q, so Q is equal to the change in internal energy minus the work done on the gas. And then I set this Q equals 0, and because that's what happens in an adiabatic process. There is no heat exchanged into or out of the gas. And I've got mc sub v dt for the change in the internal energy of the gas, and the work done on the gas is minus P dV. Then I use this equation up here, P dV equals negative V dP over gamma. So did I change the signs? I don't want to change those signs. Okay, let me just say I am a little bit concerned about a sign change here, because when I have minus P dV as the work done on the gas, that would be plus VdP over gamma. So when we do work on the gas, we're increasing the pressure of the gas. So I'm not sure about that step. Now that I look at it a little bit more, I might have a sign disagreement. But let's keep going, because they did this rho c sub p dt minus dp equals 0. So where am I going with that? We have this 0 equals, I guess I should change the signs. I'll go ahead and change the signs real quick. Plus, 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 and minus. So, and I'm not sure if that sign change is going to make any difference at all in the final argument. But anyway, we're just starting from here. MC sub v dt plus v dp over gamma. I divided out the v, so m over v right here. And the reason we did that, m over v, and rho. We changed that to the density. C sub, then what else did I do? I divided by gamma. Okay, I replaced C sub v with C sub p over gamma. So then I basically just got rid of the gammas, and we're left with dp equals negative rho C sub p dt. And so, except for the sign difference, and I'm not sure if that sign difference is going to make any big difference, but I will go ahead and write not sure if I agree. I think I do agree, but the sign difference is a little bit different. This last step was where I was like struggling to. I was like, is this accurate? Do I want to accept this? And the part that they did is they just replaced GD's, they replaced C sub p dt with GDZ. These both actually, I was like looking, are those in unit agreement? They are. GDZ, gravity is in newtons per kilogram, and then dz is in meters, so Newton meters per kilogram. C sub p is joules per kilogram Kelvin, times Kelvin is joules per kilogram, and then you're going to end up multiplying that by z meters, so you end up with, newtons per meter squared. Newtons per meter squared on both sides of this, whether you multiply rho g dz or rho c sub p dt, you end up with Newton meters squared. Then I started thinking about path derivatives because we got del z del t versus. I started thinking, well, this is an adiabatic process. What if what's really going on isn't? I mean, really, what's going on in a greenhouse gas is not really an adiabatic process. But I couldn't really come up with any reason ultimately to like imagine the gases, kind of like the way I ended up imagining the gases is that they're in any given layer, they're in free fall, so their velocity down here is going to be high, and then they'll bounce off that layer, and they'll come up here, and they'll bounce off. So they're going very quickly there, and they're going a little less quickly here, because the gravitational effect is affecting them. So I couldn't come up with any reason that they wouldn't be going faster down here than they would be up here. And so I did make it into a partial derivative, and I described the sort of the description of the path derivative is that z prime is equal to negative gt. But ultimately, my feeling is that the change in pressure with respect to z should be equal to this, negative rho g. And this comes out to be, it'll come out so that we are going to end up saying rho c sub p dt equals rho g dz, cancel out the rho's, and solve for dt over dz. It's going to be g over c sub p, which is for, since the specific heat of air is 1005, it's that's a nice round number, so it ends up looking a lot like the gravitational constant and the temperature change. It's about 97.5 Kelvin per 10 kilometers, or 9.75 Kelvin per 9.75 Kelvin per kilometer. So I was troubled by this because I was thinking, well, that seems like it's in conflict with my priors. But then I started thinking about it, and I was like, wait a second, my description was essentially that if we have the Earth surrounded by just diatomic molecules, O2 and N2, and there's no greenhouse gases in there at all, and it's lit up by sunlight, then my proposition would be that the surface temperature would be about 255 Kelvin, which is pretty cold. And but how does this idea of the dry adiabatic lapse rate, how does the dry adiabatic lapse rate affect what I've just said? Well, I'll tell you. What it does is that if we go from here to the tropopause, there's going to be a drop of almost 100 Kelvin. So the temperature out here on the surface of the tropopause then is about 155 Kelvin. So that is what your model should look like if there was no carbon dioxide in the atmosphere at all. But since there is carbon dioxide in the atmosphere, what we have instead is this situation where we have 255 Kelvin out here at the edge of the tropopause, and in here we got 288 Kelvin on average. So that is what we have with greenhouse gases, and this is what we have without greenhouse gases. Now, it should be pointed out that this temperature difference is not caused by radiation at all. All the radiation from the surface of the Earth is coming from the surface of the Earth here. This is completely transparent. This is not being heated by the greenhouse gases. This is not being insulated by the greenhouse gases. It's just that the temperature of the gases out here is going to be 155 Kelvin instead of 255 Kelvin. Now down here, though, with the greenhouse gases, the temperature down here is heated by the greenhouse gases, and the temperature up here is basically not heated by the greenhouse gases, but it creates a different surface. Okay, so now let's go back to section 4, and I guess we'll just talk a little bit more about this. It says, ever since the 19th century, when Loschmidt discovered that a thermal gradient would evolve in a solid, liquid, or gas in a gravitational field, the issue has been debated and more often than not dismissed. For example, Maxwell at the time thought it would violate the second law of thermodynamics if there were a warmer region at the base of a column of air. So based on what that said, Maxwell would have thought both of these situations were unlikely or impossible, that you could have a stable situation with 255 and 155 Kelvin without greenhouse gases, or a situation of 288 and 255 with greenhouse gases. So here we have a purely gravitational thermal gradient with no effect from insulation. And here we have primarily an insulation-based thermal gradient. We need to look more closely at this law, which was first stated by Clausius back in 1850. His statement read, "No process is possible whose sole result is the transfer of heat from a body of lower temperature to a body of higher temperature." And I would make a serious note here that the derivation of this was adiabatic process. So Clausius here, it seems like there is no transfer of heat involved here because we set Q equal to 0 in our derivation. Then he says, this statement is indeed correct if the bodies are at the same level or altitude, but we need to consider what happens when a gravitational field is present. If there is in fact a thermal gradient, then we have to explain why the original Clausius statement of the second law of thermodynamics seemed to be violated if isothermal conditions did not develop. Well, isothermal and okay, isothermal conditions did not develop. There is no transfer of heat, really. I mean, I think I should take care here not to take a good argument and make it a bad argument by getting too much into the definitions of things. My I don't want to get too pedantic over this, but when I was doing the math, I set Q equal to 0, which and the math that was done to justify the argument that we're now looking at right here. When I went through the first law of thermodynamics and I said, okay, this is an adiabatic process, so since we're using an adiabatic process, we're setting the heat exchanged to the gas equal to 0. And that was what gave us the derivation of the rest of the thing. And at the end of the problem, I said, okay, assuming no loss due to friction, which is actually, yeah, that's the nature of adiabatic. That's what adiabatic means. There's no loss due to friction. There's no heat transferred from one gas to another. But the question really is this a process at all? Is this a thermal process? Because is the transfer of energy between gases at different layers the same as the transfer of energy between gases? Is there any energy transferred between the layers? The state is called hydrostatic equilibrium. So you got the molecules in a layer will be bouncing, maybe hitting something up there at a low velocity, but boing, boing, boing. So here are the gases in this layer, and then the gases in this layer are going to be going up and down and up and down and up and down, probably hitting the layer above it, but they're hitting the layer above it with a slightly slower velocity than the layer below it. And it is reasonable to make this description, the pressure, or based on that hydrostatic equilibrium, that the temperature up here will be slightly lower than the temperature down here, because the molecules are moving less quickly here. They're moving faster here, slower here, and you'll have a vertical dependent, a height dependent temperature. But this question now does that height dependent temperature actually represent the transfer of heat from a body of lower temperature to a body of higher temperature? So yeah, so the question is the heat actually being transferred from this molecule to this molecule? And I've already stated my opinion on this. When I showed this diagram here. I said that as a matter of fact, no. The heat originated down here at the surface of the planet and is being transferred from the hot planet, 255 Kelvin, to the cool atmosphere. It's being transferred upward through that. So the heat is moving from here to here. But their principle is basically that I guess their idea is that the light interacted with the sun directly here and is then moving down and going from cooler to hotter. But I don't think that's the case. I think that the heat comes from the sun to the surface and then would transfer upward through the atmosphere from the higher, basically from the faster moving particles to the slower moving particles. But that's kind of ambiguous. Is it going from if one of the particles in a collision slows down and the other particle in a collision speeds up, which way did the energy flow? Yeah, from the faster to the slower. I mean, from the one that's slowing down to the one that's speeding up, probably. Okay, elsewhere in Wikipedia, we find a newer statement of second law of thermodynamics. It reads, an isolated system, if not already in its state of thermodynamic equilibrium, spontaneously evolves toward it. Thermodynamic equilibrium has the greatest entropy amongst the states accessible to the system. So basically, if we took this version of this with the greenhouse 288 Kelvin, 255 Kelvin, and let's say down here under the surface of the planet there was a hot spot of 300 Kelvin, and over here another hot spot of 300 Kelvin. There would be a tendency for this surface to spontaneously get hot, emitting heat that would do work on the gas and would do would do work on the gas and would heat the gas, and the system would not come to a complete equilibrium until that 300 Kelvin came into a thermal equilibrium with its environment. This version would be in thermal equilibrium because the individual surfaces would be 255, 256, 257, 258. I'm sorry, I'm going the wrong way. 255, 254, 253, 252, 251. The temperatures would be going down all the way out. And as long as they maintain that spherical equilibrium, then yeah, that would be a system in equilibrium. And thermodynamic equilibrium has the greatest entropy amongst the states accessible to the system, and basically the entropy is K sub B times the natural log of W, and in this situation that I just described down here, there's only one way that there could be a big bunch of 300 Kelvin material right there. But there are like any number of ways that that all of this would be 288 Kelvin. I mean, there's fewer ways that a heat source could be at a single location than there are ways that the heat source could be just distributed throughout the region. Physicists have realized that kinetic energy does not tell the full story. No, kinetic energy is basically the letter U. The letter U that I put here is a rotational kinetic energy plus linear kinetic energy plus vibrational kinetic energy. And that is the internal energy of the gas. And right, it doesn't tell the whole story. You need to put it together with a bunch of other things to get the whole story. As we saw above, molecules have other energy, and in particular our isolated cylinder of nitrogen we need to account for gravitational potential energy, which can interchange with kinetic energy, just as it happens when a pendulum swings back and forth or a stone is thrown into the air. So I assent to that proposition that even without greenhouse gases, there would be a gradient between the gases at the surface and the gases at the tropopause, even without any greenhouse gases, and actually that difference would be even greater than the difference that occurs with greenhouse gases. 9.75 degrees Celsius per kilometer. So I assent that we need to account for gravitational potential energy, or we can. But why have they not said that energy just needs to be conserved, as is the theme of the first law of thermodynamics? Why do we need a second law, and what is this strange abstract concept of greatest entropy, which they mention in there? Okay. So we'll get into that in the next video, whatever he's asking about there. Why do they say that we need more than one law to describe physics? Why? Okay, we'll get into that in the next video.